James Webb just photographed a galaxy cluster that shouldn't exist, not metaphorically, not poetically, mathematically. According to everything we know about how the universe grows, this thing is impossible. By the end of this video, you'll understand exactly what James Webb found, why it breaks the standard model of cosmic evolution, and what it means if the universe is older, stranger, and far more violent than we ever thought. To understand why this discovery matters, you need to understand what James Webb actually is, and what it was designed to find. Webb isn't just a bigger Hubble. It operates in infrared light, which means it sees through the dust and gas clouds that blinded every telescope before it. More importantly, it sees time. When you look at something 13 billion light-years away, you're not seeing what it looks like now. You're seeing what it looked like 13 billion years ago. Webb is literally a time machine pointed at the edge of creation. The telescope, launched in December 2021, unfolded in space like a golden origami flower, and began returning images that immediately made cosmologists stop what they were doing and quietly say, "That's not right." Its primary mirror spans 6.5 meters, almost 3 times Hubble's. Its sensitivity is so extreme it could detect the heat signature of a bumblebee on the surface of the moon. We built this instrument for one purpose above everything else: to see the first galaxies, the ones that formed in the infant universe, just a few 100 million years after the Big Bang. Small, chaotic, proto-galaxies, barely held together, just beginning to ignite. That's what the models predicted. That's what every simulation, every equation, every cosmologist expected Webb to find. Instead, it found something else entirely. Here's what the universe is supposed to look like when it's young. After the Big Bang, the cosmos was a nearly uniform soup of hydrogen and helium. Gravity, patient, relentless, began pulling that gas into clumps. Those clumps became the first stars, called population 3 stars. Enormous and short-lived. When they died, they seeded the universe with heavier elements. Over hundreds of millions of years, those elements formed the next generation of stars. Stars formed galaxies. Galaxies merged. Clusters formed. Superclusters formed. It's a process called hierarchical structure formation. And the key word there is *hierarchical, meaning it happens in order. Bottom up, small to large, slow and steady across billions of years. This process has a speed limit, and that speed limit is physics itself. To build a massive galaxy cluster, hundreds of galaxies gravitationally bound together, with a combined mass of quadrillions of suns, you need time. The math is brutally specific. You need roughly 10 to 12 billion years of gravitational merging and accumulation. There's no shortcut. You cannot rush gravity. So when Webb pointed at the early universe, at the epoch between 500 million and 1 billion years after the Big Bang, it should have seen small, messy proto-galaxies, cosmic toddlers, not adults, definitely not ancient giants. In 2023, Webb's data revealed a cluster designated SPTO 31158. Located at a redshift that places it just 780 million years after the Big Bang. At that age, it has no business being what it is. This cluster contains galaxies with stellar masses, the total mass of all their stars, that rival galaxies we see in the present-day universe. Some of these galaxies have already stopped forming stars entirely. In cosmology, we call those quiescent galaxies, dead galaxies. They burned through their fuel, formed their stars in a massive violent burst, and went quiet. And they did all of that before the universe was even a billion years old. This is why astronomers started calling regions like this the physics graveyard. Because the galaxies inside them died before they should have ever been born. The universe hadn't had time to build them. And yet there they were. Massive, ancient, dead, sitting in Webb's infrared eye like tombstones in a field that shouldn't exist. The question that nobody could immediately answer was, how? The mainstream coverage of this discovery focused on the cluster itself. But there's something even stranger buried in the data that most outlets completely missed. It's not just that these galaxies are too big. It's that they're too enriched. When you analyze the light spectrum from these galaxies, a process called spectroscopy, you can read their chemical fingerprint like a barcode. And what Webb found is that these galaxies contain heavy elements. Carbon, oxygen, iron, elements that can only be forged inside stars and scattered by supernovae. For those heavy elements to exist in those quantities, multiple generations of stars had to have already lived and died inside these galaxies before the universe was 800 million years old. Think about what that means. You need at least 2 or 3 stellar generations. Stars forming, burning for millions of years, exploding, seeding the next generation, and you need that cycle to have run its course. In a universe that supposedly hadn't had enough time for even one generation to complete. It's not just a galaxy in the wrong place. It's a galaxy that contains the asterisk history of a universe that's older than our universe is supposed to be. But before we get to what that actually means for physics, you need to understand something even stranger about where these clusters are located. Here it is, the thing the title promised. And it's bigger than one galaxy cluster. Webb hasn't found one anomaly. It's found dozens, across multiple deep field observations. Astronomers have cataloged what they're now calling universe breakers. Galaxies in the early universe that are 10 to 100 times more massive than any cosmological model predicted should exist at that time. The Lambda CDM model. That's the standard model of cosmology. The one that describes dark matter, dark energy, and the expansion of the universe. It cannot produce these structures. The simulations don't make them. The equations don't allow them. The probability of forming galaxy clusters this massive this early isn't just low. In some cases, the math returns a number so close to zero that statisticians call it effectively impossible. So what are the options? Option 1. We got lucky. We happened to point Webb at the rarest statistical outliers in the observable universe. Multiple times. In multiple directions. Possible. Unlikely. Option 2. Our star formation models are wrong. Maybe stars formed faster asterisk in the early universe. More efficiently. In denser conditions. Converting gas into stars at rates we've never seen in the modern universe. This would require rewriting large sections of astrophysics. But it keeps the Big Bang framework intact. Option 3. And this is where it gets uncomfortable. The Lambda CDM model itself is fundamentally incomplete. Maybe dark matter doesn't behave the way we modeled it. Maybe the expansion rate of the early universe was different. Maybe there are physical processes at cosmological scales that we haven't discovered yet. And option 4. The one that nobody in mainstream science wants to say out loud but that several peer-reviewed papers have now begun to seriously explore, is that the universe is significantly older than 13.8 billion years. That there was structure, mass, gravity, star formation, happening before what we currently call the beginning. Not a multiverse, not science fiction, a legitimate, mathematical possibility that the Big Bang was not the start of everything, but the start of this phase of everything. Right now, 3 independent teams are analyzing Webb's deep field data. They're cross-referencing the anomalous clusters with gravitational lensing maps, essentially using the warping of spacetime itself as a magnifying glass to measure the true mass of these objects. If the mass measurements confirm what the light already suggests, the standard model doesn't just need an update, It needs a replacement. We've been here before. In 1998, astronomers discovered that the expansion of the universe was accelerating. Something no model predicted. It forced the introduction of dark energy, a concept we still don't fully understand. To explain the gap between theory and reality, Webb may be doing the same thing right now, forcing a gap so large, so undeniable, that the next generation of physicists has to build something entirely new to cross it. The universe just sent us a message. And the message is, you don't know me as well as you think. The James Webb Space Telescope was supposed to confirm what we knew. Instead, it's systematically dismantling it, one impossible galaxy at a time. And we are only 3 years into its 10-year mission. Whatever Webb finds next, it won't be what we expect. It never is. If this broke your brain a little, subscribe. We drop one of these every week. Next week, the universe